So this hands-on session will be about something interesting that is getting very useful lately in the last years, and our machine learning potentials. And actually, you know that here some of the hands-on tutorials that you have done have been with empirical potentials or some kind of empirical potential. Most of them. Ab initio, we just did one, which was the second hands-on session that was given by Lorenzo, where you connected to the cluster, you remember, and you were running some calculations in the cluster here. But this is a real bottleneck. So the thing that is expensive with the SHA is precisely these calculations. So this is a good alternative. So George, floor is yours.
Yeah. So we will now try to fit a machine learning potential. So as Jan said, and you noticed already that the running SHA can be extremely computationally demanding. The main bottleneck in any SHA calculation is actually gathering data to do the minimization, and then later on when you have to do Hessian or some advanced stuff with spectral functions, you have to calculate very large ensembles, so many configurations, and if you try to do it with ab initio, it gets extremely difficult. Also, if you're starting from a primitive cell that has many atoms, and then you have to make a supercell out of it, the DFT is not very accommodating, so the scaling of the DFT is very bad. It scales very poorly with the number of atoms, so your calculations become very heavy very quickly. So one way, what we have found to help and to actually ease the calculation and the convergence of the results is to actually substitute the calculation from ab initio to some empirical potentials, and this is the main reason why many of the tutorials during this school is done with empirical potentials. Recent years, there is a new class of these force fields that has been used extensively, and that is these machine learning potentials. So the main feature of these potentials is that they are using a large amount of data, and they have non-parametric shape. So they can end up being very transferable and very accurate. And immediately you see the nice synergy of SHA with these types of potentials, right? Because the SHA provides a convenient way of actually sampling the Born-Oppenheimer energy surface that you need. You need this very random and very uncorrelated sampling of Born-Oppenheimer energy surface, so you have a very good training set. So SHA can provide a training set that you can calculate with DFT, and that will provide you with good resource to fit your machine learning potentials. Then you fit your machine learning potentials, and then you can calculate either higher number of configurations, or you can actually go to higher supercells and then converge the second and third order force constants. Okay, so that's what we are going to do here. It is going to be pretty simple and pretty quick exercise. So we can spend some time talking about these scripts that we have provided you with at these PDF files of the SHA school. One change that we have made from yesterday is we added 2 lines here. So if you haven't opened a new PDF file or you have downloaded the previous version from the Ehu box, you can add these 2 lines.
I think that I included those conversions in the same sample.
Okay. Okay, let's do. And if we make a mistake, it's a good opportunity to actually showcase some problems that can arise during this using this type of approach. So we navigate ourselves to the 6th lecture or 6th hands-on lecture. We can make a new folder, let's say exercise. Let's go there. And then you can copy paste the first script that I have shown on the, in the PDF file. I think we can call it ml.py. Okay. So another important point here is that this type of framework that we are going to show here is not is quite general. It's just basically a sampling of Born-Oppenheimer energy surface, and you can use it to then later on you can use whatever type of interatomic potential you want. But in this case, we are going to use the QUIPI potentials, and I think if you have downloaded all the software that using the instructions provided, that you will have it here. So here we first import from the QUIPI the function potential, which we will use to define the potential. And then, as always, we are going to load in some of the cell constructor objects that we are going to use later. Now, usually, what you will do to calculate the energies, forces, and stresses needed to fit this machine learning potential is DFT. But here, for the interest in time, we are going to use a Tersoff potential to calculate these values. One thing that you should pay attention to is that your DFT calculations have to be converged, and the DFT calculations have to be the convergence parameters used for these calculations have to be the same regardless of what type of cell shape you're using. So sometimes your training set will be diverse. You will have different phases and maybe different sizes of supercells, but in each case, you should try to keep the K-point density in the reciprocal space the same. And that's quite easily done now by the ASE environment that can automatically generate your input files. Okay, so that's when you're calculating stuff with DFT. As I said, today we are not going to do it with DFT. We are going to use the Tersoff potential, which is another type of interatomic potential, but this is quite old one. Then, so we define here this Tersoff potentials that we are going to use. It's not important right now for us. Then what we are doing, we are loading in the starting dynamical matrices that you can calculate, for example, using the FPT or some finite difference method, and then converting them into quantum espresso format. Here, this dynamical matrix will have 3 irreducible Q points in the commensurate grid, and then we load in these dynamical matrices. And now this is basically the whole point of this. We generate ensemble of configurations. We call this object ensemble train because this is the set of configurations that we are going to use as a training data for our potential. And we create this object in the supercell defined by the dynamical matrices at the temperature that we chose. And then we are going to generate for this ensemble the nconf underscore train number of configurations, which we chose to be 1000, right? And then, since we are using interatomic potential, there is a quite useful function in the ensemble object, which is compute ensemble, which automatically computes all the stresses, forces, and energies that we need, and stores them in the ensemble object. One thing here is that due to different units used in SHA and ASE, we are going to have to convert the stresses into appropriate units. Okay? Then, so we can fit our, and then obviously we save our ensemble. So we save our displacements, well, the atomic configurations, so the positions of atoms and the cell shape, with stresses, forces, and energies inside of the train.xyz file, using save enhanced xyz function that is available from ensemble object. When we are training a machine learning potential, it is always a good idea to generate a second set of configurations, which is independent of your training set, and we are going to call this set of configuration test set. That's what we are doing here. So practically, it's the same stuff that we did for the training set. So we generate an object called ensemble underscore test. We generate the smaller number of configurations for this one. We chose 500. And we compute it. We have to convert the units for the stresses. And in the end, we save this enhanced enhanced XYZ format into this ensemble into the test.xyz file. And that's it. And then we run the Python script. And of course, there's a error. Oh, yeah. As I said. So we have to. You have to specify, obviously, where you are storing the Tersoff potential, which I made a mistake previously, and also you have to specify correct path for the starting dynamical matrices. Yeah. And now the compute ensemble function is now computing all the forces, energies, and stresses that we need. Okay, so it finished. And as you can see, we have two files, train.xyz, where we have a training set, and test.xyz, where we have our test set. To actually train the potential we are going to use external code, the gap fit. And also we provided the bash script that you can use to actually fit the machine learning potential. So this gap fit is a program that should be available to you. Okay, that's not me. That should be available to you once you install the Quippy as a package. Quippy-ASE. So, yeah. And this gap fit function, this gap fit program takes a number of parameters that we can go through if you want, but they're not really important to us because, as I said, this is one particular type of program and one particular type of machine learning program that is not transferable. But we have provided also the link to the documentation for this program, and you can check what each of these parameters mean. Yes? So yeah, gap fit is basically a program that we can use to get these Gaussian approximation potentials. And these are the machine learning potentials. Basically, that's as much as you would need to know. I mean, if you want, we can go through these type of parameters if you want to. Or anyway, if you want to know in general what is the interatomic potentials. Okay. Yeah, so to run this code, we type bash train.sh. And it's going to take a while. Yeah. It's going to take a while. This is very RAM intensive code, so it might not work on your machine. If you're using virtual machine, you have to give a permission to use more RAM.
One comment here. So I think that the virtual machine that we are providing for the Mac M1 computers, which is the one that is run, I think some of you are using it. This I didn't manage to make this part. This is the only part that I didn't manage to make it work. So it was crashing. So I don't know if I think you, Jorge, you are using it, right? And somebody else probably. So I couldn't manage to make this work in that virtual machine that we are providing. But we are providing the outcome, the results in one of the files, so that you are not wrong. Sorry for the comment.
Oh. And they cannot log into the ECI and do it there?
Well, eventually they could.
Okay. Well, anyway, you're not going to use it on your personal computer. If you ever had to use this type of code, you will have to run it on a cluster. So yeah, so now it has finished, and if we check, we can see this gap.xml file, which is the files that contain our interatomic potential. Great. Okay, now we have to validate. Okay, so if you have run the bash train.sh, you should obtain these gap.xml files, which contain the interatomic potentials, and now we can validate it. And we also provided a script in the PDF file for actual checking of how the machine learning potential performs versus the original Tersoff energies, forces, and stresses. So here again, for this part, for the validation part, we again import the packages, Python packages that we need. So we are using the test.xyz file to load in the ensemble that we need, and we are loading it in a atoms object. And here we are going to print the number of configuration in the data set, in the test data set. Okay, this is, you can see the pointer. So this part, we are first defining our gap file. So the name of our gap file, which is just gap.xml, and we are loading it in using the potential function from creepy-asse. Quite straightforward. And then to actually check how it performs, we have to calculate the errors, and the errors of the predicted forces, energies, and stresses is basically the DFT calculated, or in this case, Tersoff calculated forces, energies, and stresses, minus the gap calculated forces, energies, and stresses. So first, we are calculating the DFT energies, forces, and stresses by just taking our original test configurations, which are stored in the atoms list of ASE atom objects, and we just say atom get potential energy, get forces, and get stresses. And in stresses case, we are just interested in the diagonal part of them. So we are just taking the first three values. So, and we are storing our DFT energies, forces, and stresses in the DFT energies, DFT forces, and DFT stresses variables. And then we have to calculate the gap ones. So to do that, we have to loop through all the atoms objects in the atoms list. And for each of them, we have to make a copy of that atomic configuration and attach the calculator, which is the gap calculator that we loaded in at the beginning. And also then calculate the atomic forces, energies, and stresses using the gap potential. So that's all straightforward. And then calculate the energies, forces, and stresses errors, which is basically just the difference between two. Okay, here we have just the functions, Python functions to plot the results. And also because the forces are can be ragged lists, so maybe all of your configurations don't have the same number of atoms, you have to somehow flatten these lists, and there is this simple function that does this. And we plot the results. So we are going to run this now. If I can find. Maybe I. No. I think by accident I Place caps lock. So we run this Python script. Okay, don't worry about this warning. It basically says that you're trying to use more OpenMP threads than it can. To quiet it, you can type, if you are in bash, export OMP underscore, if I can find it. Okay. Yeah, and now you will notice that the gap is much smaller than the Tersoff, which is expected, but it's way faster than the DFT, and more importantly, scales better than DFT with the number of atoms. Yes? Okay, so this is our forces, energies, and error. Energy errors, force errors, and stress errors, and they are quite bad. And we have to figure out now why, because they weren't this bad this morning. Okay, let's see. All right. Oh, did you change the? Did you trade stress? Yeah.
Yeah.
Yeah. Okay.
It's stress is changing the salient sample.
Okay. Okay. So Lorenzo decided to fix the code. So we don't have to. So here I changed the. So in this line, I actually multiplied by changed the units of the stress, thinking that the stresses had the same units as 3 weeks ago, but they are not having those units now. So we are going to delete this part, and we have to redo everything. But that's fine. It's quite quick, right?
We put a back when we're preparing this, this tutorial.
So we are recalculating everything, but and hopefully it will work this time.
Sorry, what did you change now?
So I thought, I just changed the units of the stresses the first time, and I shouldn't have done it. So also, then this means that there is a mistake in the PDF file that's online, unless you have the old version of SHA. I mean, I say old version, I think like a week ago or 2 weeks ago, 3 weeks ago. Okay, yeah. So if you have 3 weeks old version of SHA, you should have this line that I just deleted. If you don't have it, if it's newer, then you don't need this this extra line. Okay, so we regenerated, and I hope that I put append false. Yes, append mode is false. And then now we delete the old gap file. And then we train it again.
Do you need to delete the previous file, or it over?
No, you don't. But no, you don't. But it's better so you don't clutter the. If you have to share with somebody, then you have to keep in your mind which version is the current one. Okay, so now again it's going to take some time to actually fit. Oh, obviously this is just the training example. So 1000 configurations that we are using for training set here is probably not enough, but you don't really care for that. If you relaxed one of the SHA structures, you probably have more than 1000 configurations anyway. So you have enough to train. Yes. Okay, now let's try plotting the results. Yes?
Here they are trying to, what was the sport, the bash sport, or when you have this program or whatever command that you used?
Okay, let's just comment quickly on these
Okay,
results, because now they are good. So, as you can see, so on the first, the upper row of results, on the y-axis, we are plotting machine learning energy, and on the x-axis is original energy, which means that if your results are perfect, they are going to lie on the y equals x line, which is the black line here. And as you can see, for the energies and the forces, we get perfect results. This is also shown in the histograms shown on the second row. So what you want to do with this what you want to get with the histograms is the Gaussian distributions of errors centered around 0, so that you don't have that means that you don't have a bias in your training set, in your calculated energies, forces, and stresses. Unfortunately, as you can see in the stress errors, that we have a bit of skewing of the results, and this means you have to improve your training set. This can be done by either improving your training set, so adding more configurations or more diverse configurations in your training set, or changing the parameters that are inside the train.sh script. So here you can change the default sigma or cutoff for your interatomic potential, or the number of sparse configurations. But be warned, if you train this and sparse, it will become more heavy calculation. Also, Nmax and Lmax are very important for defining the basis functions of the descriptors. So you can play with these, increase or decrease these parameters to actually find the best possible interatomic potential. Now, this is all for the basic part, I think. Yeah.
Explain the thing regarding the glass.
Okay, yeah, let's explain everything. So here in this bash script, we have a number of parameters, and that you have to define to actually run the code. So here, energy parameter underscore name, we said it's energy, and this means that the code looks inside of your .xyz file for the property called energy, and that property will be associated with the with the energy of that particular configuration. The same thing is for force underscore parameter underscore name and stress underscore parameter underscore name. The virial and virial underscore parameter underscore name is for additional property that was before the same as stress. Do copy at file and sparse separate files are just parameters that.
No, he didn't. So he didn't ask about this.
Okay.
It's the problem that I have OpenMP loop.
Okay, let me see.
So, it says you did something like export
Oh my
MP
God, yeah.
thread or whatever command. Yeah.
Yeah, so it's basically export OMP underscore num underscore threads. But it doesn't change anything, it just quiets the Bornum.
Okay, no, because there is a problem in list of index out of range. So it doesn't. It's a problem in the script. Now we copy and paste the script. Not for the
Okay, okay. All right, so as I said, this is what we had for you to actually fit the atomic potential. And now, we can actually run SHA with this interatomic potential. And let's say that we trained our data at 0 Kelvin, like we did. And we want to run SHA at 2000 Kelvin, but we want to run SHA with the gap potential instead of the Tersoff potential. So we basically just, instead of Tersoff potential, we load in our newly generated gap potential. And basically all the other
I have a question about the line of port equal potential.
this one?
Yeah.
Yes?
And for the IP gap, I can write it randomly, or there's some specific name. For example, if I want to use the MTP potential, how can I write it?
No, so this potential function, or no, potential object, is loaded in from the quit underscore dot potential package. So you basically can load in only the potentials that have been coded in this package. So it is very limited number of potentials that it can learn, and they have to have a specific format. What IP gap means is that it expects the format of the potential which is given in the gap.xml. Nothing more. It is not universal. But you can use whatever ASC potential that is available. So you basically, whatever ASC potential that you can load in, I don't know if they have plugin for the ASC, you can use it.
So do you know if there is MTP potential?
I don't know, Daniel, is there MTP potential for in the asset to use with ASC?
MTP potential can be used within IC lamps.
Yeah. So yeah, that's true.
So yes, right.
So yeah, but you have to install. You have, I think, in the lamps, you have to actually provide the binaries that you can read in with Python, right? You have to compile something extra with lamps.
Yes, one should compile lamps with MTP potentials. You can read the documentation on the MTP page. I can show you the link and follow the instructions and install lamps with support of the MTP potentials and use with IC.
Yeah. So basically, yeah, that's true. Like whatever potential lamps can use, I think you can use with ASC as well.
Yes.
So it's clear?
So as I said, we load in this newly generated gap potential, and we can run the SHA minimization at 2000 Kelvin starting from the starting dynamical matrix. Here are some general properties of the SHA minimization coded in. If you have any extra questions that you forgot to ask in the previous days, you can ask them now. And then basically, when we finish our VC relaxation, so that means you are relaxing also the structure at zero pressure, in this case. You can save the final dynamical matrix, and you can plot these results. Now let's see how it does. Okay, again, I forgot to actually provide a correct path for the starting dynamical matrix. Okay, yeah, so because we are using 1000 configurations, it's going to take some time to actually calculate the configurations needed for this ensemble. But once they do that, the SHA minimization can continue. Is there any questions now while we wait? Okay.
So do you have a feeling or some general suggestion on how to tune the parameters for the gap fit to get good results? How do they depend on the system that you're trying to train?
Well, for the gap potentials, basically what you want to do is to increase the N max parameter, and then increase the L parameter as well. But that's one thing. But I think the most important part is to actually have a very good training set. So the training set is the part that you have to worry most about. But there are, like, it's a trial and error. You have to do it by hand. Try different combinations of parameters, and hopefully you will get the precision that you want. So yeah, here it might take some time because we are calculating at 2000 Kelvin. Maybe that was a mistake, but we want converged results, right?
How can you check how free energy after minimization is gap and is DFT or those here we use Tersoff as a reference, and how this energy like differ after the SSCHA minimization relaxation?
Well, yeah, that's one of the checks that you can perform, and it's actually a pretty good check. Is to actually do this minimization using interatomic potential, and then once you get your minimum of the free energy, you recalculate it with DFT and see how close you are to the actual minimum. You can do that, yeah.
I think it would be a good test about how much configuration one can use to.
Oh, you mean?
Or training on the like potential like the soft or other.
Yeah.
And just to see how much configuration you need to train.
Yeah. You can do that. So yeah, that's another thing. I don't know if yeah. So if you use this, the reason why it's quite useful to use this machine learning potential is that SHA uses a lot of averaging, and if you have these normally distributed errors, you kind of hope they will cancel itself out in the end. So your results shouldn't differ that much from the DFT, right? Because most of the errors are actually being cancelled because they are not biased. Or at least you hope so. But the best thing you can do is actually test your final configurations.
Which was the comment with open?
It's export. Well, if it's bash, it's export space OMP underscore num underscore threads equal 1 to quiet the warning. And also, once you generate these gap potentials, then your bottleneck actually becomes the SHA minimization. So if you use very large supercells, so that means a very large Q grid, then the main bottleneck becomes the actual minimization and not the calculation of these forces errors. Yeah, so we have finished, hopefully. Our unit cell has expanded as we would expect at 2000 Kelvin. And now, okay, no. And we have generated 10 populations to actually converge, and the final dynamical matrices have been saved in the final _DIN file. Now, we have left as an exercise. So this is what Daniel was asking. Now we have calculated our structure at 2000 Kelvin. There is a question if these interatomic potentials do a good job. So one of the exercises that you can do is to actually check how this gap potential performs for this system. So for this final DIN system at 2000 Kelvin, and compare the gap potential versus Tersoff, which is our benchmark. Once you do that, you can see that the errors, I expect you to see that the errors have increased from the initial check. So I expect that the errors on forces, stresses, and energies are larger for this test set than for the test set that we have previously calculated. So then is the question, how would you improve this gap potential? So you can do that and check that. If there are any questions and any queries, I'm here to help. Yes?
Just a technical question about the output format of this train potential.
Oh, yeah.
This is quickly pairwise format.
Yeah, so it's like this.
Yeah, but I mean,
So the .xml files contain the potential, but they have some numbers. I don't think they are human readable.
because Quippy,
Yes?
from other fields, but Quippy can be very useful to run in these simulations, and it works with many codes basically.
Yeah, you can use this.
There is a format, the pairwise format of this potential, and then it can be basically used for any.
Yeah, definitely. This potential can be used to run MD simulations, for example, with lamps, definitely. So you can do that.
If you train this empty simulations, or am I missing something?
No. So what SHA provides is basically a way to sample uncorrelated structures. For example, if you run the MD, so you have to run MD for certain number of steps so that your neighboring configurations are not similar. In SHA, you don't have to worry about that because they are randomly generated, so they are all uncorrelated, and hopefully they are sufficiently different from each other to actually be useful during the training process. Yeah, all of this that we have done here can be done with MD simulation. It's just going to take a bit longer. Yeah.
Thank you so much.
And obviously, once you generate the interatomic potential, you can run MD with it as well. So.
More questions or comments? Someone is trying to do the exercise actually, or you are very tired? Yeah, you have one of you has the problem with the units, and you have the problem with the units in the stress, and you don't have the problem with the units in the stress.
Yeah,
Yes.
they probably have different versions of the code.
Maybe you downloaded the link or at a different moment. So maybe you installed the circumstance. I think this is in the Python shower or the circumstance. I don't know where. You downloaded it at a different moment after we corrected the code. Yeah. Đorđe, in which package is this unit change coming?
I don't know the latest commit on the.
No, but in which this is the constructor or this is the?
Oh, I think ensemble is in cell constructor. Yeah.
It's a constructor.
No, Lorenzo.
Lorenzo. The units problem. This is fixed in is Python SHA or is cell constructor with this?
Python SHA 1.3.2 fixes.
Okay. Python. So you need to update the Python SHA.
Here we use supercell is 3 by 3 by 3.
It could be 3 by 3 by 3 or 2 by 2 by 2. I think they have the same number of irreducible points. So both of them, I think, have 3 points in the reducible. So it's easy to check. I mean.
How much training, how much time for training would it take for large unit cells and large supercells? For example, with
You mean
several tens of atoms, with, for example, 50 atoms or 20 atoms. How would you scale this number?
Well, there are different things that slow it down. So the number of configurations is usually more important than the number of atoms in the single configuration. Number of configurations that you actually put in the training set also. Then there is also the cost of the DFT calculations. More atoms, they are more costly. So there are different costs. I don't know which you mean. If you mean just the fitting of the potential using the gap fit function, usually it takes me half a day to train a potential. But number of configurations, maybe 3.5 thousand. Yeah. But yeah, it depends how concerned you are about the later on how heavy the potential is and how slow it is. Yeah.
This is have it is only for monatomic systems or for
No. We have run it. We have run it for different classes of materials, monatomic, diatomic, etc. Yes.
One question.
Yeah.
According to your experience, so how many different elements? As far as I know, there are limitations when you go beyond 3 or 4 elements. I might be wrong. It becomes very complex and difficult.
Yeah, I don't know. That's the limit I tried. So yeah, I tried mostly the most number of different elements inside the compound that I tried is 3. So I haven't tried larger, more diverse systems. So I don't know. But yeah, my experience, I didn't see a lot of difference between d element and 3-element systems. But I could be wrong, right? I mean, it's not my. I use it, but I use it from case to case when I need it. I don't actually do any coding or I do any extensive searches using the machine learning potentials. Okay, so this is the solution of the first exercise. So we generate, so I can go back. So basically what I changed is in the first script that we used, I changed the dynamical matrices that we use to generate the training and the test from start underscored in to final dot underscored in, which is the dynamical matrices created at 2000 Kelvin with the gap potential. And basically everything else stayed the same, except here, instead of append mode false, we changed it to append mode true to actually add these new configurations from this new ensemble to the old training and test sets. And we didn't retrain the potential to check how it performs. And if we, as I said, if we if we recalculate the new, if we compare the new configurations with the gap potential and the Tersoff, we see much larger errors. And most importantly, we see that they are not for energies, I think, and for stresses, they are not Gaussian anymore, and they are, I think, for energies binomial. Yeah, as you can see, so here, this peak in the distribution of errors comes from the original set, which was very good, and it was a Gaussian centered around 0. And as you can see now, we have, this is the new set, the training set calculated with the dynamical matrices generated by the gap potential at 2000 Kelvin. And as you can see, for this part of the test set, we have much larger errors. Also, for the forces, they seem centered around 0 because you would expect that, because the atoms can go left and right, and depending on which way they go, you will have plus minus error. But more importantly, you can see that the standard deviation of these errors is increased. And also in the stress, you can see a binomial distribution. So this first peak comes from the original test set, and the second peak comes from the second set generated by the final. So what you want to do now is obviously that your gap potential that we created at the first instance is not good enough to model the dynamics at 2000 Kelvin. So you want to retrain this machine learning potential and recalculate the dynamical matrices at 2000 Kelvin. And this is the iteration that you do several times until you reach a good potential. Yes?
If we train the gap potential initially or at 2000 Kelvin, would we have a better
Yes.
results for 1000 Kelvin?
Yes. If the original dynamical matrices and the original configurations were performed using the dynamical matrices calculated at 2000 Kelvin, this wouldn't change at all. So the energies and the stresses and all the other properties would have the same error as in the first case. So yeah.
I mean, maybe it is better to start training at high temperature and then.
Oh yeah, So this is just to showcase. It is just an example of when this type of procedure can fail and what is the cause of it. So it is just like a warning for everybody who plans to use it to actually check the convergence of this machine learning potential. Not convergence of the machine learning potential, but its applicability at this situation that you are using it for.
So this means that it's not at all transferable what we created at 1000 Kelvin at 2000 Kelvin, right?
Yeah. Yeah, well, this means you have to check it.
Yeah, okay.
And then you will see if it's usable or not.
Sorry, I missed a certain point. So you created at a certain temperature.
Yes.
Then you test it with a higher temperature, it failed. So what is what you have to do? Not just redo it again.
Yeah, you just have to. So you have to calculate new training set at this temperature, add it to your previous set, or discard the first set and just prepare the data from the current temperature and refit your gap potential. And then do this iteratively until you reach self-consistency in your interatomic potential.
Why you say that's what I don't understand? Why you say iteratively?
Well, you maybe so. So we started at 0 Kelvin.
Yes.
We fitted the interatomic potential. Yes. Then we use that interatomic potential to generate dynamical matrices at 2000 Kelvin. And now it's bad. So we refit it at this 2000 Kelvin. We again relax with this new potential at 2000 Kelvin. Now we have moved somewhere. Then you check and it's again bad. So you moved here, and yeah, this is where the self-consistency comes in play.
Just another thing. So this gap is just a specific kind of.
Yeah, we use gap is because it's the only one I used before. So I'm pretty sure there are people here who have used more different interatomic potentials than me, and it's just to show people how efficiently SHA can be used to actually sample the Born-Oppenheimer energy surface. And
So you can use also the same kind of.
yeah.
Okay.
Yeah.
I mean, this is something I would like.
Okay, thanks.
There is hope here to train a potential that works at 1,000, 2,000. Yes, right? So you do this process iteratively. You did it and it works?
Yes.
Yeah. So this is the exercise, right?
Yeah. Yeah, this obviously, where this comes into play, and it's very useful if you want to simulate a phase transition, and this is where I use it mostly. I want to simulate a phase transition, and what I do is I start from the configurations from each phases, all phases, and then iteratively improve the training set and calculate the interatomic potential until I reach the sufficient accuracy of the interatomic potentials, and then I use SHA to actually trace the phase space and calculate the phase diagram of the material system, using the Hessian to check for the dynamical stability, and using the calculated free energies to actually check for the first order phase transitions. So this is what I use it for. Some people might have different plans. For example, to check the convergence with respect to the Q point grid, commensurate Q point grid.